So in this example, we're going to take a look at spherical capacitors, and I want to point a couple things out here. That first of all, the inner conductor of this capacitor we're going to consider to be negative, and this is still a ideal Gaussian symmetry, so we'll be using Gauss's law, and we'll be using the spherical symmetry of Gauss's law, the surface area of a sphere. So this problem, it's going to start just like any other, and it's going to be C is equal to Q over delta V. And of course, delta V is unknown. So for that, we go to delta V is equal to minus the integral from A to B of E dot ds. And E still is not known as a function of position, so we have to find E using Gauss's law. So we use the integral of E dot dA is equal to Q enclosed over epsilon naught. Now, we've already said before, our Gaussian sphere is this, and everywhere along that Gaussian sphere the electric field is constant, and the surface area of the sphere is 4 pi r squared, so we just get E times 4 pi r squared for the left side of Gauss's law. Q enclosed is going to stay as Q, and that's going to be over epsilon naught, so E is equal to Q over 4 pi r squared epsilon naught. Substitute that back into our equation for delta V. We get delta V is equal to minus the integral from A to B of Q over 4 pi r squared epsilon naught dr. And all of this is constant except for r. And so when you do the integral, you're going to get this negative, and when you integrate 1 over r squared, you're going to get another negative. So those negatives are going to cancel out, and you're going to have Q over 4 pi epsilon naught r evaluated from A to B. But before I go any further, let's recall that this is a negative charge, and therefore we're going to put another negative back onto that. So we get delta V is going to be equal to minus Q over 4 pi epsilon naught, and then for R we're going to write B minus A. Now finally, we just substitute it back into our definition for capacitance and simplify. So we get Q over minus Q divided by 4 pi epsilon naught times B minus A, and the two Q's of course cancel, and we get C is equal to 4 pi epsilon naught over 1 over B minus 1 over A, and when we throw the negative sign on here, the B and the A's are going to switch positions, and we get C is equal to 4 pi epsilon naught divided by 1 over A minus 1 over B. And that's it. The spherical capacitor was not nearly as bad as maybe it sounded in the beginning. In fact, most of these capacitor problems are really quite straightforward. It's just the little things that they slip into it to make it just a little trickier.